So we're about, no, I don't want AI. I don't know about you, but I started using AI at work a little bit, and it's very depressing. Like, it's very, what? It feels like you're just wasting your time. Like, the code is writing itself, and like, why am I here? You know, I don't know if you felt that way, but it's good, I think, if you know what you're doing already, but if you don't know what you're doing and it's writing the code for you, then you're not going to learn anything. So, right. I'm not sure what the point of that is. Okay, there we go. Oh, you could be able to find it. Hey, good. You see?
Vacation with
Oh,
the next year.
okay. What people would want.
Oh, okay.
I don't know if it works.
Okay. Hmm. Hello, everyone. My name is Anthony, and tonight for my presentation, I'll be covering 5 different data mining techniques to turn your raw data into useful insights. And so there are many ways to mine data, but tonight I'll be focusing on 5 of the most common data mining techniques. And those are classifications, value predictions, clustering, associations, and visualizations. So to make it easier to follow along, I've organized them into groups by their operations or their functions. So I'm going to start with predictive modeling techniques. Then I will follow up with segmentations and link analysis techniques. And then I will finish it up with deviation detections. So predictive modeling, as the name suggests, predictive modeling techniques is we use historical data to predict future outcomes. So classification is a technique that categorize each data point to make predictive decisions. So for example, a very common example would be your email inbox. Every time you get new emails to your inbox, usually there is some sort of models, typically called the decisions tree modeling, which looks like a tree. And so the model will look for the sender, the email subjects, any attachments, any particular keywords, and then it will try to predict whether the email is a spam or not. For numerical data, we can use what is called predictive value predictions techniques to estimate a continuous numerical value. So for example, when we want to try to predict a weather temperatures for tomorrow or for the next few days, we can use statistical regression models to try to predict based on the past weather trends to try to make a weather forecast for the next few weeks for that temperatures. So basically classifications techniques, it's trying to categorize, well, for example, in the email, whether it's a spam or it's a valid email. And for value prediction techniques, they'll try to do numerical calculation data, such as whether it'll be 60 degrees next week. So another use case for data mining techniques is to organize data. Clustering is a technique to group data points into segments or clusters with similar attributes. So for example, in marketing, many times we always want to, they do a lot of what is called segmentations of their customer base. And usually, for examples, if we take a look at their demographics, usually we may find sort of a correlations, for examples, between their education levels and their income levels. So you can see that sometimes they are kind of grouped together. Um, there is a tendency where if you have a higher education, there is a tendency that you may have higher incomes. Not always, but there tends to be a tendency. Association techniques. So this is type of a link analysis in which the technique is trying to find any kind of relationships and dependencies within the data. So what's very well-known example is called the market basket analysis. So in these examples, usually we will look on customers' past purchases, and from that data points, we will try to see if there is any sort of relationships. So for example, usually if a customer buys milk, they tend to be more likely to buy cereal. So in this, the model will find there is the associations or relationships between milk and cereal. Finally, visualizations is a technique often used to try to detect any source of deviations. Sometimes it's a lot easier to check for any anomalies by just simply visualizing the data. So for example, in this example, if we map out somebody's purchases and we sort of see an unusual purchase in California when usually they do their purchases in New York, it's a lot easier to see visually that there is some sort of a deviations in this case. So to summarize, whether we are predicting weather, segmenting customers, or trying to detect some sort of a fraud activity, these 5 techniques are really essential tools for turning your raw data into useful insights, which usually in large organizations, they will use it to help make some sort of a better informed decisions. That's pretty much it. If you're interested to learn more, dive deeper, there is a course CSCI 334 here at Queens College for data mining. Thank you.
I don't know who signed up.
No.
Okay, look at everyone. Did you sign up?
Yes.
Okay. Sign up. Okay, like, cause no one was doing it for a while, and all of a sudden. Anyway. Okay.
Hello everyone, my name is Vikas Shrestha. Today I'm going to talk about how DevOps and CI/CD make software development faster. So let's start with the introduction. DevOps is a set of the practice that combines software development and IT operation. It aims to shorten the development cycle and deliver high quality software continuity. And let's introduce about the CI and CD, a continuous integration. In continuous integration, developer frequently merge code changes into the shared repository, followed by automated builds and test. And continuous development is automatically develop code to the production and reduce the manual intervention. So how DevOps speed up development? So it encourages collaboration between the development and operation team, automates infrastructure providing and configuration, provisioning and configuration, reduces bottleneck and improve communication. How CI and CD accelerate delivery? It automated testing, ensure quick feedback, continuously development, reduce release cycle, and minimize human error and speed up delivery. So benefit of DevOps and CI/CD is it's a faster time to the market, improve software quality, enhance scalability and reliability, and increases customer satisfaction. So in conclusion, DevOps and CI/CD practice significantly accelerate software development by automating process, improving collaboration, and ensuring continuous development of high quality software.
How does it make it high quality software?
So because it is a collaboration between DevOps. It's a collaboration between the developer and IT software, IT operation that been said. So developer is like getting continuous feedback. So what is getting wrong and what need to be improved. That's how it. Thank you.
Thank you. Oh, wait. Shrink that. Same key thing. You just do that. Might come back. Hit escape key.
One second, sorry. Hi everyone. Today I'm going to compare two major agile frameworks used in software engineering, such as Kanban. Flip it. Yeah, it's too small, right?
No, could you
Zoom it in.
Yeah.
Yeah. For some reason it's not allowing me to. Why isn't it? Is that good?
Yeah.
Gotcha. Hi everyone. Today, I'm going to compare two major agile frameworks used in software engineering, such as Kanban and Scrum. Both of them fall under the agile umbrella, but they differ a lot in how teams plan work and how they are used and to deliver work and how they manage workflows. By the end of this presentation, you should have a clear understanding of how these are used in the work environment. And yeah, so let's get started. A little bit too. There you go. So before talking about Scrum and Kanban, we need to understand Agile itself. So Agile is not a single process, it's a philosophy and a set of principles for building software in an iterative way. Instead of big, rigid plans, Agile encourages teams to build software in small increments, get feedback quickly, and also adjust as needed. Agile focuses on collaboration, working software, and responding to change rather than sticking to a fixed plan. This is all dynamic. Under Agile, there are multiple frameworks: Scrum, Kanban, XP, Lean, and others. But today we're only going to be focusing on Kanban and Scrum and talking about the differences. So what is Scrum? Scrum is the most structured and formal of the two frameworks. Everything in Scrum happens in fixed length iterations called sprints, usually lasting between 1 and 4 weeks. At the start of each sprint, the team commits to a set of tasks called the sprint backlog that they believe they can finish by the end of the sprint. They set realistic expectations. So Scrum has very clearly defined roles. The product owner who prioritizes the work, the Scrum Master who makes sure that the team follows the Scrum process, and the development team who actually builds the software. Scrum also requires certain artifacts like product backlog, sprint backlog, and an increment, which is the final result of the sprint. So Scrum events. Scrum also includes a set of structured meetings called ceremonies. So first, sprint planning is where the team chooses what work will go into the upcoming sprint. Then the daily scrum, also called the stand-up, is a quick 15-minute meeting where the team shares updates and identifies blockers. And at the end of the sprint, there's the sprint review where the team shows what they completed to the stakeholders. Finally, there's a sprint retrospective where the team itself reflects on what went well and what went bad, and what they can improve on for the next sprint. These ceremonies help keep communication consistent and make sure that the team's continuously improving. So now onto Scrum workflow. So the Scrum workflow goes through a predictable cycle. First, the product owner prioritizes the items in a product backlog. During sprint planning, the team selects a group of items and commits them to finishing them during that sprint. So once that sprint begins, the team solely focuses on those selected items. No one should add or remove work from the sprint after it starts. Throughout the sprint, progress is tracked using tools like burn down charts, and at the end of the sprint, the team has an increment, which is potentially shippable product or update. Then the sprint ends with a review and a retrospective, and the cycle repeats. This predictability makes Scrum ideal for feature-driven development. And what is Kanban? Kanban is extremely different. While Scrum is built around fixed sprints, Kanban is built around continuous flow. There are no sprints, no required time boxing, and no required meetings. Work moves through the system one task at a time as the team has capacity. So Kanban focuses heavily on visualizing work using a board, limiting how much work is in progress and reducing bottlenecks. And instead of pushing work into the sprint like Scrum, Kanban is a pull-based system. So when a team member finishes something, they pull the next item from the queue, and Kanban is much more flexible and adapts easily to constantly changing priorities. So Kanban board and workflow details. So a Kanban board is the core system. It consists of columns that represent different stages of work. For example, to do, in progress, in review, testing, and done. Tasks move from left to right across the board as they progress. And Kanban has a few key principles. They visualize the workflow, limit work in progress, manage flow, make process rules clear, and continues to improve. The most important of these is limiting work in progress. When you limit how many tasks can be done in a column, the team is forced to finish work before starting something new, which improves the flow and reduces bottlenecks. Okay, the key differences. So now here's the Scrum and Kanban really diverge. Scrum is iteration based, while Kanban is flow based. Scrum is fixed in sprints, while Kanban is continuously delivers work, and Scrum requires defined roles, specific meetings, while Kanban does not require any of those things. In Scrum, once a sprint begins, you are not supposed to add new tasks. In Kanban, new tasks can come in at any time as long as the team has under their work in progress and their limits. They also measure performance differently, such as Scrum uses velocity and burn down charts per sprint to measure how much work is being done, while Kanban focuses on cycle time and lead time throughout the entirety of overall throughout. And overall, Scrum is more rigid and structured, while Kanban is more flexible and adaptive. And how is work planned and managed? So in Scrum, planning happens at the beginning of every sprint. The team estimates their capacity using velocity, then chooses the work they believe they can finish in the sprint. Once the sprint starts, the work is locked. This prevents interruptions and keeps focus stable. Kanban takes the opposite approach. There's minimal loaded planning. Instead, the team prioritizes tasks continuously, and people pull new work as soon as they finish what they're currently doing. Kanban is much better suited for teams dealing with unpredictable work schedules like bug fixes, support tickets, or operation works. So the difference lies in commitment, while Scrum commits to a batch of work for a fixed period. So Kanban commits to keeping workflow smoothly at all times. Metrics and performance measurement. Scrum and Kanban also differ in how performance is measured. Scrum relies heavily on velocity, how many story points the team completes every sprint. It also uses burn down charts to show how much work remains in the sprint, and burn up charts to show how much progress has been made. Kanban focuses on flow efficiency. Lead time, it measures how long it takes from the moment a task is requested until it's completed. And the cycle time measures how long the team actually spent on working on the task. Kanban teams often analyze cumulative flow diagrams to spot bottlenecks and process overall, while Scrum measures predictability, Kanban measures speed and flow. When to use Scrum and Kanban. Scrum is the best choice when their work is predictable and can be planned ahead. If your team is working primarily on new features and stakeholders want to see progress every couple of weeks, Scrum is ideal. The structure of sprints and ceremonies helps keep teams disciplined. Kanban works best when when work arrives unpredictable, sorry, or changes their frequently. For example, in IT operations, DevOps teams, customer support, or bug fixing teams, these teams can commit to two batches a week, because new priorities might come in at any moment. So the choice depends on the nature of the work. Planned feature-based work aligns with Scrum, while constantly shifting interruption-heavy work aligns with Kanban. Summary and key takeaways. To just wrap this up, Scrum and Kanban are both agile, but they serve different purposes, such as Scrum is structured around sprints, roles, and ceremonies. It's predictable, organized, while Kanban, on the other hand, is based on continuous flow, flexibility, and reducing bottlenecks. It's lightweight and adaptable. And many companies today even combine the two into what's known as Scrum Ban, using the structure of Scrum, but the flow management of Kanban. Ultimately, the best framework depends on what your team needs and what they're currently working on. Yeah, thank you for listening.
I'd just like to give class a little bit, and then at the end, we'll have another two presentations, okay? There are two more people, right? So, am I right? Two more people presenting? Okay. Right, right there, at like 9:30, okay? I'm sorry, yeah, about 9:30, right? Okay, so I just wanted to cover some stuff. Um, okay, okay. Oh, you gave the best explanation of Kanban that I've heard, because I don't do Kanban, so where I work, so I know Scrum, but I didn't know Kanban that well. Give a very good explanation. So, um, do you work in a job?
Yeah, I'm currently a part-time engineer at a startup company.
At a where?
At a startup.
Oh, they use Kanban or?
Yeah.
Oh, yeah? Well, okay. So you know from experience, huh? Yeah. Yes, especially a startup, there's always interruptions, right? Okay. Okay, so I just wanted to finish. Okay, so first we were doing we're in the middle of doing architectural patterns, right? So we're nearly done. So we already discussed three-tier, the whole idea of having a tier, right? Well, which tier is at the bottom? What's top and what's at the bottom? How do you decide which is the top or the bottom? Right? The one that in other words, the one at the bottom is the one that it's not dependent on anything else, right? And then the one above it is dependent on all the ones below it, right? So, like for example, over here, the web layer or the presentation layer dependent on the two below it. And the middle layer is dependent on only one, right? But you could have 8 layers, right? And then the top one's dependent on everybody below it, right? So you know, it's it depends on how many layers there are. But the idea is the same, is that the bottom layer is always going to be the one that has no dependency, that could exist by itself, right? And we said that when there's a change to the layer, what gets affected? The layers, right? Let's say I change the presentation layer, what could get broken? Could I break any of the other layers? No, right? Because nobody's dependent on it. But if I change the bottom layer, I could break. Yeah, well, for sure, I should check the layer above it, right? And I might even have to go further up. But for sure, the one above it could break. Theoretically, you only need to check the one directly above it. Um, where I work, we have like 21 layers or something like that. Well, I shouldn't say layers, but they're used like layers. Like we have like projects. We don't really call them layers, but the idea is that we have like low level database stuff and then a little stuff above it, and there's utility, So we go up in layers. I don't know, maybe not so maybe it depends where in the code, but we do have a lot of layers, so if you change so we try not to modify. If you try to modify a bottom layer, you might be breaking something above it, right? But if you do something on top, you're not going to break the database layer, for example, right? If I change how a screen looks, I won't break the database, right? Or I won't break the logic. Okay. Um, Then we spoke about how the non-functional requirements um, decide the architecture. Okay, meaning that you would think that how a system is and again, we're not talking about design patterns, we're talking about architectural patterns, right? Which is different than design. Design pattern is just discussing, the way we design the actual coding, the classes, how they interact and stuff like that. Here we're talking about the whole program, how the parts of the program, the different modules interact with each other. So if the non-functional requirement of your program, right, is to have performance. So then you like we gave an example. So then a Tesla, which needs high performance, meaning it has to self-driving car. If you're driving any self-driving car, right, or anything that an airplane or rocket ship, anything that's moving really fast, you have to make a decision right away, right? You don't have time to communicate with another module that's on the internet somewhere else, right? Though I heard they just did an operation like remotely. Did anybody hear about that? They did surgeons in England operated on. I think it might have been not a person, but maybe an animal. They operated remotely. So so that would be like kind of scary, right? Because if the internet goes down in the middle of the operation, well, yeah, so that would be a little bit scary. But that's the idea that if you need performance, you want your architecture to be tight, right? It doesn't mean it has to be like physically in the same project. It just, because that doesn't make it slow. If you could have 20 projects, like what I do, where I work, we use what's called a solution. So we have like 32 projects or something like that in one solution. So I don't think there's any slowdown if it's in different projects, but 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 there would be a slowdown if they were in different machines, right? And the machines would have to speak to each other, or let's say some of the logic would be in the database, and you have to query the database to get some information, and then based on that information, you would have to react or something like that. Um, so that would be if you need a fast program, which is a non-functional requirement, right? Because it's not specific to any part of the program. It's a general thing about the program. So then you need you need everything to be important decisions to be made, internally, right? Within the same module. Okay, meaning architecturally within the same, meaning like on the same machine or the same program, right? Where there's no delay. Okay, then we spoke about security. So if security, like every website, it pretty much needs to be secure, right? So it actually depends. Like Wikipedia doesn't really have to be secure, does it? I don't know, right? Or Google, why would it have to be secure? You're not really. Um, I mean, I guess it has to be secure because you don't want people seeing what you're searching for, maybe. I'm not sure why you would need, maybe that would be a reason to be secure, but really it's just read only. So, you don't have to sign in really to use it, right? Or any store, right? If you go to Macy's.com, you don't have to sign in, right? So, but if you need security, meaning you don't want people, um, like you want you like it's a let's say something like a company web company application where like people working in this company sign in, let's say Social Security, right? You want to sign into your Social Security to look at your benefits or whatever, or you want to, or you log into Queens College, whatever. If you work here in Queens College, you want to see what's going on with your benefits, for example, so like an HR type of thing. So those things would be, you would need you generally you would have the architecture would be that you have to sign in, right? And then it would have to authenticate to check who you are, right? Um, oh, let me just write this down because it's actually interesting. There's authentication. Does anybody know the difference between authentication and authorization? So authentication means that um, means that meaning that we verify the user identity, right? In other words, we want to verify, let's say we call your phone, your cell phone, and we verify that you're really who you say you are. Authorization means, well, just because we know who you are doesn't mean you could use our program, right? Or you could use everything in the program, right? Usually, people have different roles assigned to them, right? So, verify or only um, allow user to permitted areas, right? So that would be authorization, right? You have to be usually a website will first authenticate, right? Make sure who are you, right? How do I know you're not a Russian something, right? Right? Then after I know who you are, I have to check what your permissions are. Usually most programs don't allow everybody full access to everywhere on the program, right? Nearly every program will have different roles, right? What's it called? Role-based permission. I forgot what the acronym is. It's called RBAC, maybe? Role-based access or access control list. Um, I forgot. Well, but basically that's the idea. Um, Usually nowadays we give roles. So like somebody is the admin, so if they have that role, they have permission to certain areas, right? Because it's a lot easier to do that based on roles than remembering, oh, this guy got promoted to a new position. Now I gotta, let them see this page and that page and that page, right? That's the way it used to be, right? But now we just do roles, meaning that this role has could see these screens, this role could see these screens. So then you just change permissions by roles. So did anybody cover this in another class? I mean, another course about rule-based permission? It's important to know. It's called, I think it's called RBAC. But when you come to a company, it might even come up in oh, yeah. Role-based access control. Okay, so that's RBAC. So that's very common in, most programs, right? That your people are assigned one or multiple roles, and based on their role, they could access different features. Okay, so it's called role. I'll just copy this part. I actually had to do something similar to this in my company. Um, why doesn't it let me copy it? Okay. Oh, here we go. Okay. Okay. Um, okay, so that's very common. Nearly every, if you don't do that, then it becomes very, very chaotic, right? Okay, now safety is different than security. So safety means, security means we want to keep our secrets safe, right? That's sa security. Safety, on the other hand, means we actually don't want to kill people, right? So if we write software for let's say for a pacemaker, a heart pacemaker, you don't want it to accidentally not work when it's not supposed to. Uh, I mean, when it's supposed to, or work, like it shouldn't go off by accident, you know all of a sudden shock somebody while they're walking down the street, by accident. So safety is basically, or, it means that you actually mean safety and no one should get hurt. So, so when you're dealing with safety, they recommend, so any type of software deals with safety, they recommend so we're not so much worried about speed as we are worried about that we understand what's going to happen, right? Like like sometimes I think like now Tesla uses they have AI, and I think they changed their model, the self-driving cars. Like I think they used to use like rule-based programming, and then they realized, and now I think they switched to AI, which is basically they don't know what's going on, right? They're like, they have they have the software learn by itself what to do. So you really don't know what's going on inside in the program while it's making certain decisions. So, um, so then it's really hard to analyze this if it's really safe or not, right? So so the idea here is that at least when this book was written, maybe now it's really changed with it, but like I'm not sure how you could rely on AI to, let's say, drive a car. Like if you don't know what it's based on, like, you know. No, yeah, maybe it is safer. I don't know. They say the AI self-driving car software from Tesla works better. So, um, but when this book was written, he said that it's more safe if you understand everything, exactly how it works. Okay, so I would feel safer with this. Yeah, like people say these self-driving cars are safer, but when something goes wrong, it goes really wrong, right? So like people are afraid of going on the airplane when really the most dangerous part is the the trip to the airport. Driving in the car to the airport is the most dangerous part, really, not the flight. But since when something goes wrong, it's so scary, so people think about the flight as being dangerous, right? When really statistically, it's more dangerous to get in a car, right? Um, so I think the same thing with AI. When AI goes wrong, it's more scary to people because, it like seems so obvious that it should not have happened. Okay, maintainability. Okay, now this is very interesting. If you want your code to be maintainable, which means what? To be easy to maintain means to what? To maintain means to what? Maintain. To come on, fix, right? If you want code easy to fix, right? Which most programs, like that, because usually you have to fix it, right? If you don't have to fix code, then you don't care what it looks like, right? Because it's written and it's there, right? If you're writing code and you're putting in, say, it's a refrigerator or a microwave, then you don't care what's in there because it's never going to change, right? That you sold that microwave, that refrigerator, you're never going to, change the chip that's running it, right? So you don't care. But in general, you care about the code because you want to update it, upgrade it, whatever. So it turns out that the way you should design is that the module should do as little as possible, right? Because if you hit I always bring this as example, like where I work, like we have very few methods that have more than a couple lines of code, because the idea is when you split up code into small pieces, then first of all, it's obvious what the code does, right? Because you could see it's only doing like two or three, a couple lines of code. And number two, it's also easy to make a change because you see what the change is going to do. You only have to change so if you make a change, you're not changing, something like somebody wrote something that literally was 150 lines of interconnected code. It was like one huge loop. I don't know it was like the craziest thing I've ever seen. And I even knew what was wrong with it, his code. I figured out the problem, but I couldn't figure out how to change it. I was scared to change it. So it was like so complicated. So the less complicated something is, then the more easy it is to change. So if you want to write maintainable code, make everything small, right? You have code just exactly what it needs to do. And and then when you change it, you're just changing a line over here, a line over there, and there's much less chance that you're going to break something, right? As opposed to if you have a lot of lines of code, then there's more of a chance that you'll break it. So it's very interesting that yeah, like what I mean, obviously when we have like a lot of code that's just one line of code, but it's not I mean, it's not just one line, I mean, one line sounds like it doesn't do much, but some of those lines, there's a lot packed into one line. You could put, yeah. But the idea is to be easy to modify. So people could look at the code easily, see what it does, and change it, knowing what's going to happen. Okay. And over here, I just went through a couple popular architectures. So this is NLayer, right? Where we spoke about, different layers. So these are different types of applications that have it. I mentioned at the beginning the 3-tier because those are the ones that I've worked with most of my career. Client server pattern is basically anything that communicates with a server. So for example, email, document sharing would be like Google Docs, right? Where you upload the document and it's shared among, you could share with other people or Dropbox, banking, right? All those, or a database. So all those things are client server, right? So that's pretty obvious, right? Because you have a server with the data and you're connecting to it from your computer. So you're on the client and the server is in the cloud somewhere, right? So, right, so that's pretty much all new software is like that, right? Though I spoke to somebody, they told me that video games are still computer, they're not in the cloud yet, right? They're still, you have to download it, install it, right? I mean, I don't really play video games, so, but that's what I was told. But pretty much everything else is in the cloud, right? Most business software is ending up in the cloud. Okay. And okay, there's another pattern here called pipe filter. And this idea of this is that the output of one is the input to the next. So the architecture is what they call filters, but because it's based on like Unix. But the idea is that you have one program and the output of one program is the input to the next program. So the way you architected the program is you have a bunch of different executables, and each one is spitting out something that goes to the next executable, which spits out something which goes to the next one, which either is the end or whatever, right? So for my favorite example of this would be well, besides Unix, but I don't think people really know Unix. But besides Unix, I would say, let's say a compiler, right? So if you're familiar, let's say C++, right? So in C++, what do you have? You have first you have the preprocessor, right? That's one program. And then the preprocessor converts it takes in all the header files, right? Whatever it is, you don't have to know like exactly. But the idea is that there's a bunch of programs, right? So if in C++ you have header files, .h files usually. So those files that you include at the top, those are going to be merged at compile time into one big file. And then that one big file is compiled into a object file. And I think C++ there's two steps. It goes from C++ to C, and then from C, it goes into an object file, and then the object file gets combined by a linker into an exe. So you see very well that you start with a source file, and you go through a preprocessor, a C++ to C converter, a C to binary converter, and then a linker that puts it all together, makes an executable. So that would be, there you see the output. So you could change any executable in the middle if you want. Like, for example, you're not forced to use the same, let's say I could change my linker, right? As long as it takes in a certain input and gives a certain output, I could change the preprocessor, right? I could swap it out if I want to, right? Um, I remember when I used to write C code that I remember there were different linkers you could use. You didn't have to use like only one, right? As long as it knows how to combine object files, you only have to, you're not stuck with the same manufacturer that made the compiler. You could use a different linker, which might be more efficient and make a smaller, let's say, executable or something like that. Okay. And then there's another architecture which we really don't have nowadays, except for Bitcoin, where you have, which I really don't understand, but basically the idea is that each computer is a client and a server, meaning that I don't understand how it works, but I guess one computer is mining and the other one is they're communicating with each other. I don't know how they work, but the idea is that it's kind of dangerous because basically you're opening up your computer to other computers. You're like a server for other people, and this is not really a server, it's really a PC, right? So sounds kind of crazy. I mean, it used to be, but I think they used to be like they used to download movies, right? And basically, they used to have like basically like I forgot how it worked because they made it illegal. But it used to be that you would download a movie onto your computer, like half of a movie onto my computer, someone else's computer, and then other people would download it from us or something like that. So, but I think they made all that illegal. So, um, okay, finally, okay, we get to the MVC. And the reason I'm mentioning this is because it's a very common pattern. It's very similar to the pattern up here. Okay. Um, Over here at the top, we have 3-tier, which is the presentation layer. And then we have the application layer in the middle. And then we have the database layer at the bottom, right? So we divide it up into those 3 layers. And MVC also has three layers, but it's a little bit different in that there's no because the MVC is how it's not really showing us basically if you have a web program, right? The MVC describes the desktop, the server portion of the code, how it's broken up. So there's so when I'm looking right now, this is not a browser, but let's say over here when I'm looking at a browser, right? So over here, I'm just looking at the code that's sent to me by the web browser or the JavaScript, whatever it's running, or whatever was sent to me, right? So, but what's happening on the server itself, right? So typically on the server itself, they use there's a famous pattern called MVC, which I don't know if it's so popular anymore, but does anybody else know any other patterns, architectural patterns on the server? This is the only one that this used to be very popular. I'm not so sure it's still popular, but but basically the idea is that you would have what's called the controller, which would get the request from, we're talking about, so again, MVC is only on the server, right? Only server portion. We're not dealing with what the person's, what I see, right? We're talking about how the server handles requests for information. So the way it works is the controller gets the request and then it hands off the request to the model, and then so the model handles that, and then gives a response back to controller, and then the controller doesn't directly respond, but really sends the information to the view portion of the server, which formats it according to the client. So basically, if you have like a smartphone and your screen is very small, everything's between the controller and the model will be the same, but the view might give you a different response, right? Based on the size of your screen or the browser or um, um, what's it called? The resolution, right? So based on those aspects, the view might give you the different type of web page, or will probably give you, or maybe even different JavaScript, whatever. So that's basically how it works. Okay. So that's if you go for a job interview, they might ask you about the MVC, though I'm not so sure it's still popular. It used to be very popular. Let me just do a quick search, see if it's still popular. Um, MVC popular is um, still relevant. Uh, yes. Uh, okay, it says it's still relevant. I'm not sure, but because I think it's used by, it was, oh, okay, so it is still popular. Okay, good. I don't want to teach something that's not popular. Okay, but if anybody knows of any other architectural patterns that they think are important, let me know. Okay, okay, so we have two more people to present. Okay, so who are those? Okay, so sorry to do it then, but I want to make sure I covered the chapter. Um, Okay, so next we're going to skip chapter 7 and we're going to move on to 8, which is testing. Okay? Um, okay, and then, okay, come on. What's going on? Okay. Uh, there we go. Okay, okay, here you go. Working a little slow. Am I running out of my battery? Let me make sure my battery is still, uh, let's see, what is that? I think it's okay. I think we have enough. I think give me a warning. Oh, sure.
Hello everyone. Today I'm going to talk about the difference between generative AI and regular AI. I will focus on the key concept and the real world application. Let's get started. So first, let's look at what is regular AI. Regular AI mainly focus on the prediction and decisions making. It learns patterns from existing data and use them to classify, detect, or recommend things. For example, the spam filter can predicting whether an email is spam. A fraud detection model can finding the unusual transaction, and recommendation system can suggesting movie that you may like. The main idea is the regular AI does not create new content. It analyzes what it already exists. In contrast, generative AI is designed to create things. It can generate text, image, code, audio, and based on what it has learned from huge data set. Tools like ChatGPT for text, Stable Diffusion for the image, and GitHub Copilot for the code. The idea of generative AI is create new things that it didn't exist before. Here's a simple way to compare the two. Regular AI focus on predicting outcomes using existing data. It's usually used for tasks like classification and or regression. Uh, Generative AI, on the other hand, it creates new content. It uses large models that learn patterns and generate output that didn't exist before. In short, regular AI equal to predict and generative AI equal to create. In real life, these two types of AI are used in different areas. Regular AI is used in things like medical diagnosis, uh, credit scoring, and navigation systems. Generative AI is used in chatbots, image generation, and code generation. Both are becoming important in software engineering, but they solve different types of problems. To summarize the main idea, regular AI analyzes data to make predictions. Generative AI learns from data to create new content. Both are powerful, and understanding the difference help us to choose the right tool when building software. Thank you for listening.
Very good. Okay, one more person. Mm,
Hello everyone. I'm going to,
just those three dots and hide the floating in the trouble.
what was it?
You would hit the three dots in the bottom. You could hide yeah,
This?
click that and hide. Well, yeah, get rid of that.
Is that good?
Yeah, right.
Okay, so hello everyone. And I'm going to be talking about whether or not adding more team members always speeds up development. And the short answer is no. And I'm going to be explaining why that is and how it ties into real world applications. So let's start with the common assumption. So most people think that the more people you have, that means you'll have more productivity. And that makes sense in a field like construction, for example, where you could have multiple people operating machinery at the same time. But that doesn't apply in software in the same way. In software, it actually behaves differently. So instead of speeding up productivity when you add more people, it actually ends up slowing it down. And that's because new people coming in need to be onboarded, right? They need to learn the architecture, they need to learn the tools, and they need, to be caught up to speed with the developers that are already working on the project. So this means there's a lot of back and forth going on. And instead of, the main developers continuing to finish what they were doing, they now have to stop and train the new developers in order for them to catch up to speed. But deadlines don't move. So as the deadline approaches, they are not going to be able to finish. And so they either have to rush to get it done, which means the quality is going to be less, or they miss the deadline entirely. And by the time the new developers are done with onboarding, they would have missed the window to be able to contribute. And that is what's known as Brooks Law, which states adding manpower to a late software project makes it later. And that is specifically true in the case of adding people in the middle or the end of a project, because at that point, the code base is already very complicated and it takes time for someone new coming in to digest and know what's going on. And as you can see from the graph here, the lower amount of people you have at the beginning means the time to complete is less. But as you continue adding more and more people, the time goes higher. So then the question becomes, is there a moment in time where adding people is actually beneficial? And the answer is yes. And that is right at the beginning of a project. And this is because the system is very simple, right? No coding has begun. So you can distribute the work evenly and everyone can contribute effectively, as well as since not a lot of no code has been done, that means everyone is on the same page. No one has to catch up with someone else or someone else has to train someone else. So everyone is growing together and they're growing with the project together. And it can tie with Agile because if the project is using Agile methods with small independent stories, that means that they don't need to know the entire code base. They only need to know a part of the code base to be able to contribute effectively, which means it increases productivity. So in conclusion, adding team members late does not equal faster progression. It actually slows it down. And so you want to really add people only at the beginning because nothing has been really coded yet. And you can decide right there whether or not you need more people, because adding more people later on can effectively postpone when you're going to get your project done. And that's it.
I've actually seen in companies when project is behind, the hire consultants. And that's exactly what happens. Usually it fails by then. So, okay, so Thursday, okay, so see everyone Thursday. And we'll do chapter 8, right? Testing. Okay. And okay.